Gradient descent explained like you're 5. Well, kind of. You kind of need to know a little bit more than a 5-year-old. You kind of need to know a little bit of differential calculus, but I'll hopefully make it very, very simple for you regardless. Alright, in this video, we'll be covering the gradient descent algorithm. We'll be covering two very, very important learning parameters, learning rate and training epochs. We'll be going over some problems of gradient descent and how to implement the algorithm in Python. Alright, I'd like to start by giving you a little bit of intuition. Let's start with how does an AI learn? Well, let's say you have an AI model that's trying to predict the prices of an Amazon product given a set of parameters. So the way that it learns is that it first takes a random guess. So, maybe it would predict that a microwave cost about $1,000. And that we know as a human that's really far off. Here in Australia, you can actually get one for about $50 to $100 from Kmart. So $1,000 is really far off. But the second step is to compute the loss, and the loss is really just the difference between your initial guess and what the actual value is. So we guess 1,000, and maybe the real value is about $100 to $200. And then you tweak the parameters so that the loss is reduced. Because we made this initial guess is $1,000 for a microwave. That's really bad. But we want to get better and better and better until we eventually get pretty close to the actual value. That's kind of how an AI model actually lands. And if you actually do a quick search in Amazon, you would actually see this. I don't know if it's still up, but in Amazon Australia, you can see this microwave up for sale for about $2,500. I don't know if I would ever buy something like this. It sure does look like a very, very, very high-end microwave, very professional indeed. But as far as I'm concerned, a microwave typically costs about $100 to $200. But anyways, to give you a bit of a visual cue on those three steps. So when you have this, let's say you have this set of data, your first step is to take a random guess, and it's gonna look really, really bad, but it might actually look pretty good in the first step as well, because it's all random. But anyways, let's say this is your initial guess, it's pretty bad, but you compute the loss, and then you try to tweak the parameters, and you do some black magic, and we'll cover what that black magic actually is in a little bit. But you do some black magic to like update the parameters of your model, and then the next time you go through the data set again, it's gonna look better, and then you repeat those steps until it looks better and better and better until it eventually gets a pretty good fit at the data. So that's kind of how an AI learns. Towards uncovering the black magic that we know as gradient descent, which is what makes AI be able to learn, I'd like to first introduce the loss function. Here on the left, you can see a plot where the y-axis is L for loss, and the x-axis is theta for the parameters of our model. And you can see here L of theta, which is just a function of the loss. So, intuitively, if you want your model to be as accurate as possible, well, you want the loss of your model to be as small as possible, right? You want to minimize the loss. So your whole goal in deep learning, really, is just to somehow get a value of theta over here, because at this point, the loss of your model is at the minimum point of your loss function. At this minimum point of the loss function, the loss of your model is minimized, the error is minimized. But again, recall from earlier, the way that your model learns is it first takes a random guess at the parameters. So maybe we start over here. Maybe at this point, we guess that a microwave costs $1,000 and a laptop costs $30. And as you can tell, this is complete bogus. Nobody sells a laptop for $30. But I mean, if you're actually selling a laptop for $30, I mean, hit me up. I'll buy 10 of those for real. But again, this is complete bogus as far as I'm concerned. But so our goal is to somehow get our initial guess over here all the way to this point. And maybe at this point, it would look something like this. These inferences look a lot more, reasonable. Maybe you can get a MacBook Air with $2,600. But how do we know where that point is? Where the minimum point is? Well, recall from differential calculus, at the minimum point of a curve, we know the gradient is 0. This orange line over here is L prime, which is the derivative of the loss function. And as you can see, when the loss function is at the minimum point, its gradient is 0. So our goal is to somehow get this, our initial guess over here to be to jump from here all the way to the minimum point. So we do that by subtracting from our parameters the gradient of the loss scaled by some learning rate. And this learning rate is a very, very, very important training parameter, which we'll cover more on later. But all it does is determines how big of a jump you make. So, maybe our first jump looks something like this. But why does this work? How do we know where to move? Why are we moving towards the right direction? And why aren't we moving towards, the right here? Well, because at this point, the gradient is positive, as you can see here. And so we'll be subtracting from our theta, which is positive, a positive gradient scaled by some learning rate. So theta will be smaller, and so we'll be, going to the left. But say we started over here. Well, at this point, the gradient is below the x-axis, as you can see here. It's a negative gradient, so we'll be subtracting from theta, our parameters, a negative gradient. So that becomes addition, right? So theta would be larger, and we'll be moving towards the right. So that's kind of why this formula works. And essentially, we just keep repeating that until we converge. We say that we converge towards the minimum point where the loss is minimized. And one last thing I'd like to point out is that as you move closer towards the minimum point, your jumps become smaller and smaller, as you can see over here. And that's because, the gradient is becoming smaller as you move towards the minimum point. Now, I'd like to touch more on learning rates and also another training parameter, a very important training parameter, we call training epochs, or simply epochs. So earlier I said that the learning rate is simply how big of a step you take. Because remember, all we use it for is just to scale down the gradient of the loss by which we subtract from our parameters theta. So what if the learning rate is too large? Well, maybe you can already see where this is going. When the learning rate is too large, we might see a humongous jump like this. Let's take another jump. Oh no, we're going over the minimum point. We're overshooting the minimum point. And let's take another jump. We keep going over it again. And so it seems like we're never going to reach the minimum point because we keep going over it. And let's consider another case where the learning rate is also too large. And maybe you can also already see where this is going. The initial jump is going higher. So let's take another jump. It's going even higher and higher, and you're escaping the learning rate. You're literally escaping the hole. And we say that we're diverging. So learning rate should generally be a small number, like 0.01, because the goal is to converge towards the minimum point, and you wouldn't wanna, skip over the minimum point. But what if it's too small? And can it be too small? And turns out, yes, it can, because you might actually reach the end of the training, because by the end of the training, we might not even reach the minimum point if the learning rate is too small, because you keep taking this very, very, very tiny steps. But what exactly does this end of training mean? Well, to answer that, I'd like to address this other training parameter called the epochs. This is essentially how many times the data set is passed through during training. And just for the sake of discussion, I'd like to use the term batch gradient descent, which you can think of just taking one step for every epoch. So one epoch equals one step. There's also variants of gradient descent, which is a lot more advanced, where for every epoch you take more than one step. But for the sake of discussion, let's say one epoch equals one step. So if you set the epoch parameters to be the training epoch parameter to be 3, well, you would be taking 3 steps. And if you set it to be higher than that, however many this is, it seems like 7. If you set it to 7, then you'd have 7 steps in your training. And so I hope you can already see the problem here. We've exhausted our training epochs. We've reached the end of our training epochs, but we haven't reached the training the minimum point because the learning rate is so small. We keep taking too tiny of a step that we weren't able to reach the minimum point by the end of the training epochs. So all of this implies 2 points. As a rule of thumb, if you increase the learning rate, it makes sense to use fewer epochs in order to avoid divergence. So you don't keep overshooting the minimum point. But if you decrease the learning rate, it also makes sense to use more epochs so that you give the model more time to converge. Let's go over some problems of gradient descent. Now, just as a heads up, I'll probably be a bit hand-wavy in my explanations of the solutions to these problems, because frankly, a lot of them kind of require that you know a bit more advanced topics, all of which are outside of the scope of this video. But I like to cover the problems nevertheless because I think they're pretty important. The first one is multiple local minima. So your loss function might look something like this. You know, that's multiple local minima, multiple minimum points, multiple points with a gradient equals to 0. But this one is obviously not as good as this one. This is the global minimum point. This is where you want to go. Now, I hope you can imagine that if you have a tiny learning rate, it becomes very easy for you to be stuck in one of these local minima. On the other hand, if you have a larger learning rate, you might actually be able to jump over some of these local minima. Another way you can also escape a local minima is using a concept known as momentum, but I won't be covering that in this video because it's kind of out of scope. Now, the good news is there's usually very few local minima in high dimensional space, which is likely to be the case for your dataset when you're making deep neural nets. Now, another problem is saddle points. So this is a point over here where the gradient is 0, but it's neither a local minimum nor a local maximum. It's a local minimum in one direction, this direction, and it's a local maximum in the other direction, this direction. So, you know, your algorithm might go from here, might start here, and then go down and down and down and down and down, and then be stuck in here, thinking it's a minimum point, but it's actually not. It's just a saddle point. Now, a noisier version of gradient descent known as stochastic gradient descent, SGD, might solve this because essentially you'd be taking a more zigzagged approach, something like this, and you know, as you can imagine, zigzagging might actually help you escape a saddle point. Another way you can escape a saddle point is using a concept known as adaptive learning rate, but I won't be covering that in this video. Here's two more problems. So on the left, you can see our guess starting over here, and it's moving down, and you know it's doing pretty good so far, until it stops moving, or maybe it's still moving, but it's barely moving because you know this is practically almost a horizontal line. The gradient is very close to 0, so it's practically stuck, and this is what you call a vanishing gradient. Here's another illustration. So in this case, you might already start to see what the problem is. You know, this is a very steep line, and once you start going around this area, boom, you're teleported. The gradient was so large in magnitude that it overshot the minimum point. It's so steep, it's almost a vertical line, as you can see here. You know, the gradient was so large that it skipped over the minimum point. And this is what we call exploding gradient. So let's look at how we can implement vanilla gradient descent in Python. So this is our loss function, and this is the derivative of our loss function. Now, if you've forgotten your differential calculus, our loss function is a polynomial, and the way we get the derivative of a polynomial is for every term, we multiply the term by its exponent minus 1. So for example, we got this term by multiplying x here by 2, which is the exponent, and then subtracting 1 from 2. So you get 2 times x to the 1. And then, of course, you drop the constants. And here we're making a range of numbers from 0 to 10 with 400 points in total, equally spaced. We're just doing this to make a line for visualization's sake in the next code chunk over here. So this is a plot of the loss function. I'm using w instead of theta for the parameters of our model, and also j instead of l, which is, you know, j of w is kind of a convention in some areas of machine learning. Again, to remind you, the algorithm goes something like, first, we start by choosing a random guess, maybe here, but essentially we'll be trying to get that guess all the way from where it initially was all the way to the minimum point over here. And the minimum point seems to be at 4 when w is 4, and it's the loss over here is actually also 4, although you can't really see it very well over here, but it's, you know, optimally equals to 4. Now this is the part that matters the most. So, you know, we start by making a random guess between -10 and 10, and then we set our training parameters. We set learning rate to be 0.1 and then epochs to be 20. We'll try modifying this later on. But this is the bulk of our algorithm over here for gradient descent. For every epoch, we get the gradient using the derivative function, and then we update the parameter x, which was initially whatever we get here. We update that by subtracting from it the gradient, the current gradient, scaled by the learning rate 0.1. Let's try running this. So as you can see, we initially get the x value negative 1.65, and at that point the loss is 36. And we keep updating for every epoch until we eventually reach x 3.93, where the minimum with the loss at that point is 4, which is pretty close. The actual value is 4, but we got 4 point something. So we were able to reach convergence. And as you can see in this plot over here, I'm just gonna plot the convergence. Yeah, we were able to reach convergence. Now, what if we try changing the learning rate to be, let's say, 0.01? So earlier we discussed that if the learning rate is too small, we might not be able to reach convergence, because by the end of the training epochs, we were taking too tiny of a step that we weren't able to reach the minimum point at all. Let's try doing that. And that does happen, as you can see here. Our local minimum turns out to be 18.27, when the actual value is actually 4. So we're not able to reach convergence. Now, what if we try to set epochs to be, let's say, 100? Maybe that's enough for us to reach convergence? Question mark. Not quite, but we were able to get a lot closer than earlier. We got to 4.56 or something. But yeah, I hope that kind of gives you the idea how you can implement vanilla gradient descent in Python. Now, in practice, we use more advanced optimizers than the gradient descent algorithm. But the idea behind it all is still gradient descent at the end of the day. So I hope this was an enlightening video, and I hope you learned something from it. So yeah.